call is now being recorded.
Hi, good morning all. Welcome to Mount Zion College of Engineering, Kadammanitta, Pathanamthitta district. We all have here for a webinar on analog and digital circuit simulation. I am Shinu James, Assistant Professor, Department of Electronics and Communication Engineering. I am here to welcome our speaker and also our participants to this webinar. First of all, I would like to welcome Mr. Arun Varghese, Associate Professor, RIT College, Kottayam. He is our speaker for our today's webinar on analog and digital circuit simulation. I welcome Arun sir to this webinar.
Thank you.
Secondly, our participants, the success of a webinar or an event depends upon the participation of the people. Here we have a good number of participations from many colleges. Here mainly faculties, students, all are attending this webinar. So here I would like to welcome all the participants, which include faculties, students, industrialists. I welcome all of you to this webinar. We will start our section now. Arun sir will continue the section. Thank you.
Thank you, Shinu. Thank you.
Thank you, sir.
So, welcome all participants to this webinar on circuit simulation. So, all of us have been learning from the comfort of our homes. We have been learning a lot of theory, but what about laboratory? So one thing that we may have missed during this time of home learning could be laboratory practice. So the question is, can we get some laboratory practice also from the comfort of our homes? So the answer is yes. If we have access to a computer and a circuit simulation software, we can get, to a certain extent, at least we can get some laboratory practice and learn some good laboratory skills from the comfort of our homes. So I wish to introduce a software called Multisim, which is a circuit simulation software. So Multisim is just one of the many circuit simulation softwares available in the market. If you do a Google search on circuit simulation software, you will see many results like Proteus or ORCAD or LT Spice or NG Spice. There are many software, and Multisim is just one of them. But there is a lot of similarity among all these circuit simulation software. So that means that if you learn how to use Multisim, you wouldn't find it difficult to switch to any other software, say ORCAD or NGSpace, because all these softwares are actually based on the SPICE software, which was created way back in the 1970s in the University of Berkeley, California. So all these modern software, underneath the skin of all these software, we have the same SPICE, or it's some of the spin-offs called PSpice, but the original SPICE was text-based. But modern software like Multisim is graphical, which means that you create the circuit in the circuit window using a computer mouse. You draw the circuit with a computer mouse. But the original SPICE was text-based, which means that you had to describe your circuit and its connections using text. So, but clearly describing the circuit by drawing the circuit on the screen with the mouse is more convenient. But even now, underneath that, the graphical user interface, we have the SPICE. We have the SPICE, same SPICing. Another point is, all these are very similar, and you won't find any difficulty in switching from one software to another, say from Multisim to ORCAD or say Proteus. So So I've even though I've picked multi-sim, so don't consider that as a limitation. You can, once you learn how to use multi-sim, you can switch to any other software. Okay, so let me share my screen now. Hope my screen is visible. So let me turn my video off. So let me start multi-sim. So here you see that multi-sim is a product of National Instruments. This was actually created by another company called Electronics Workbench, which was later acquired by Multisim. And you may have heard the name Multisim because Multisim is a major player in the electronics education industry. Another software from National Instruments is the LabVIEW, which you may have heard. And Multisim is also a popular software from National Instruments. So this is a little bit old version of Multisim. If you do a Google search for NI Multisim, that will take you to the downloads page where you can download the software. You can see that the latest version is Multisim 14.2. I am using version 11. So you can download it and install it. But Multisim is not a free software. But you can use the trial version for 45 days or something. But I am actually using a cracked version, version 11. So if you search the internet, you'll be able to find cracked versions of earlier releases of Multisim. So if anyone is interested in installing this software, I can provide version 11, which is for our purposes, this will serve. No need to, there is not much difference from the latest version 14.2 from this version 11, which I am using. So if anyone wishes to install Multisim, you can contact me. I'll share the software with you. Also have the crack. But anyway, I don't think that National Instruments will take that using the cracked version seriously because we are using for educational purpose only. Moreover, it's an old version. So far I haven't heard any issues about software piracy. So this is the window that you see when you start Multisim. Okay. So this is the circuit window where you have to draw your circuit. Okay. So you have to pick components from the component toolbar. Okay. So this is the component toolbar. So you pick components from the component toolbar, drop it in the circuit window, connect them together, and you simulate the circuit using this run button. Okay. On the top you have menu bar, and this menu items. Some of the menu items are similar to other Windows applications, while some are peculiar. You don't need to know all the details to get started with Multisim. You will gain, as you get some practice, you will gain familiarity with the items that you need to know. Okay. So this is the component toolbar where you pick components from. You can see that the components are divided into various groups. Okay, source, basic, diode, transistor, analog, TTL, CMOS, miscellaneous, digital, mixed, indicator, power, advanced peripherals, RF, electromechanical. NI has its own components, microcontrollers, and so on. Okay, so Multisim has a very large component database. Yeah? So it's very unlikely that you will find that the component that you need is not available in Multisim because it has a very large database. So, and on the right you see the instrument toolbar. Okay, you have a multimeter, function generator, watt meter, oscilloscope, 4-channel oscilloscope, board plotter, frequency counter, word generator, logic analyzer, logic converter, distortion analyzer, spectrum analyzer. So Agilent function, even Agilent multimeter, Tektronix also. So if I click on the Tektronix oscilloscope, I place it in the circuit window and I double click, you see the front panel of a real Tektronix oscilloscope. All these, this is model 2024, and you can click on these controls. You can turn on the oscilloscope, and so this is like actually having a real Tektronix oscilloscope in your home. Okay, so you can operate on all these controls and learn the operation and the function of all these keys with this virtual Tektronix oscilloscope. So that is one advantage of having a simulation software, because we know that electronic lab equipments are very costly and we cannot buy this set up a big very good electronics lab at our homes. But the availability of a simulation software like this, with this software you can learn very good laboratory skills, and uh, uh, and and this is especially important if you are designing a new circuit. Okay, so because in that case you can easily change component values simply by the click of a mouse. But if you have physically constructed the circuit, say in a real laboratory, changing component values and modifying the circuit design, that is a tedious process. But when you have access to a simulation software like Multisim, modifying the design or changing component values is very easy. It can be done simply by the click of a mouse. And you also have access to all these laboratory instruments. So you can do your first design with the software like this. And then once you have satisfied with the input and by output, by verifying the simulation, you can prototype the circuit on a real breadboard. Okay, and the sister software of Multisim. When you install Multisim, you also get another software called Altiboard. So that also gets installed. So you see Altiboard. Altiboard is a sister software of Multisim, which allows you to generate PCB layouts. Okay, so the circuits that you have designed in Multisim can be exported to Altiboard to generate PCB layout. So that's another feature of Multisim. You can feed the circuit to downstage steps like PCB layout. So Altiboard is also available along with Multisim. Okay, so, but we will not be generating PCB layout. We will be simply be creating and simulating circuits using Multisim only. But remember, that is also possible. You can for the circuit that you have designed in Multisim, you can export that circuit to Altiboard, which will generate the PCB layout, and you can that PCB layout file can be used to manufacture the actual PC. So that way, simulation offers lot of convenience. Okay. So let us start with a simple circuit. Let us start creating a very simple circuit at first. Let us start with a voltage divider. Okay. So voltage divider, I need a one voltage source and two resistors. Okay. So I click on this source button. That opens the component browser. Okay. So you can see that the master database is divided into various groups. Okay, sources, basic diodes, transistors, etc. Okay, and when I click on the source group, we can see that sources are then further divided into various families: power sources, signal voltage source, signal current source, controlled voltage source, controlled current source, controlled function, then digital sources, so on. Okay, let me choose the power sources family, and within the power sources you see various components: AC power, DC power, digital, ground, and so on. And within that, let me pick a DC power. Okay, so remember that the master database is divided into various groups. Each group is subdivided into various families, and within each family we have actual component. For example, if I within the master database, if I select a transistor group, I see that within the transistor group, I have various transistor families like BJT, NBN, BJT, PNP, Darlington, MOS, JFET, so on. So we have different families. And within the, say, I pick the BJT, NBN family. Within the BJT, NBN family, I see all the BJT, NBN transistors available within multisim. See, this many BJT, NBN transistors are available. So you can imagine the total number of components available in multisim. Okay, within the transistor group, within the BJT, NBN family, I have this many transistors. Okay, so say I want to pick a BC107 transistor. So I'll type BC here. So the components get filtered out. I pick a BC107, click on OK. So now the component browser opens again to pick the next component. I'll click close here. So I have placed a BC107 transistor. So anyway, we are going to wire a voltage divider. Let me delete this component by pressing the delete key on the keyboard. And let me pick a voltage source and two resistors. Okay. So for that, within the source group, within the power sources family, I pick a DC power. Click on OK. So when you do that, a DC power source get attached to the mouse cursor, and you simply have to place it wherever you want it to appear on the circuit. So you place it wherever you desire in the circuit window. I place it here. So the component browser opens again to pick the next component. So now I need two resistors. Resistors are available within the basic group. So I click on group. I switch to basic. So I see resistors here. So I click on the resistor family. Within the basic group, you see resistors, transformers, capacitors, inductors, so on. Variable capacitor, variable inductors, so on. So I click the resistor family, and you see all the resistor values available here. I can pick the exact value, but I can also change the resistor value after I place it in the circuit window. So I don't bother about the actual value. So this value is 220 ohm. I pick one more resistor. I pick one more resistor, place it in the circuit window. Now I need a ground also. For simulation, multisim requires that all circuits should have a ground. So ground is within the sources group. So within the sources group, within power sources, I pick the ground. Okay. So ground also I have picked and placed in the window. So these are all the components that I need to wire the voltage divider. So I click close. Okay. So now I need to wire these components together. So to wire, I have to bring the mouse cursor near the terminal of a component. I want to wire from here to here. So when I bring the mouse cursor to the near the terminal of a component, I see that the mouse cursor changes to a plus. It changes to a plus side. So that means at that point you can start a wire. So when I click that, a wire gets attached to the terminal. Wire gets attached to the terminal. You simply have to click again at the terminal where you want to end the wire. So I want to connect this wire to the left terminal of R1. So I simply click here. So now the wire has been attached. Now I want to connect the right terminal of R1 to the left terminal of R2. So again, when I bring the mouse cursor near this terminal, we see that the shape of the cursor changes to a set of crosshairs. So that means I can start a wire at that point. I click, the wire gets attached. I don't have to drag. I can simply click where I want to end the wire. I want to end it here. So I click here. So a wire has been connected. Next, I want to connect R2 to the lower terminal of V1, the negative terminal of V1. So for that, I can click here and simply click here also. Then multisim will choose the wire path for you. maybe I want to fix the wire path myself. So that is also possible. So in order to fix the wire path, if you click somewhere, the wire gets attached to that point, gets fixed to that point. So say I click here, wire gets fixed here. Say I click here, wire fixed here. So again I click here, fixed here. So that way I can control the wire path also. Okay. So by clicking, wire gets fixed to that point. So that way I can control the wire path also. So otherwise multisim will choose the wire path for you. So let me delete this. To delete a wire, you have to select the wire and you can right click and delete, or you can simply select the wire and press the delete key on the keyboard. That also deletes the wire. So let me wire it little bit neater. Click here. So I have connected this. Now, as I said, multisim requires that all circuits need a ground. So I need to connect the ground to this point, ground to this wire. Okay. So one thing you should remember is that we cannot start a wire from the middle of this wire and end. And you can you have to start a wire from the terminal. Okay. And I can end on another wire. I can end on a wire, but I cannot start a wire from the middle of a wire. So I start from this and click here. So the ground has also been connected. Now, as I said, even after placing components in the circuit window, I can change the component value. Say I want to change these R1 and R2 to 1K. So for that, I select this. And if I double click, that opens up the component properties window. Here you can change the label, say R1, you can change the name under the label tab, and under the value tab, you can change the value. Okay. So I'll change it to 1K. You can change it to 1K. Or you can use the pull down menu to change the value. I change the resistance value to 1K. Click on OK. So R1 is now 1K. Maybe I want to change R2 also to 1K. So type 1K. So now R1 and R2 are 1K. Maybe I want to change this to 10 volt. Say select, simply you double click on that. That opens the properties window for that particular component. And I can change the voltage to say 10 volt. Maybe if I want to change the label, I want to call V1 as VS instead. I want to call VS. So I change the label. So now V1 has been labeled to VS, and I have the voltage divider. So now I want to measure the voltage across R2. So I want to measure the voltage across R2. For that, I pick a multimeter from the instrument toolbar. Okay. As I mentioned, we see the instrument toolbar at the right here, and I pick a multimeter here. So I place the multimeter here, and I connect this multimeter across R2. I connect the multimeter across R2. So now I can simulate this circuit. You can simulate the circuit by clicking on this play button. So when I click that, you can see that the circuit is being simulated. You see that design one is being simulated. And in order to see the voltage across R2, I double click on this multimeter. You can see that the voltage is 5 volt. Voltage is 5 volt across R2. Okay, because R1 and R2 are same. This 10 volt divides equally between R1 and R2. So I have 5 volt across R2. Okay. So maybe I want to change the resistance value and see the new voltage across R2. I want to change R2 to 9K and see the new voltage across R2. For that, I have to first stop the simulation. Okay, circuit can be modified only if it cannot be modified when it is being simulated. So I have to first stop the simulation, and then only I can modify the circuit. So for that, I click the stop button. Now the simulation has been stopped. Now I can make the modification. I double click on R2 and change it to 10K. Change R2 to 10K. So I want to simulate again. Click on the play button. Now I can see that. Oh, sorry. Let me change it to 9K so that more. So you see that voltage across R2 is now 9 volt. Okay. By voltage divider rule, this 10 volt divides 1 volt across R1 and 9 volt across R2, 9K. So I see that voltage across R2 is now 9 volt. Okay. So now I want to maybe I want to measure the current in this circuit. Okay. So again I have to connect the multimeter in series with R1 and R2. So to make that modification, again I have to stop the simulation first. I click on the stop button, stop the simulation. I have to connect the multimeter in series with R1 and R2. So let me delete this wire. I select that wire and press delete on the keyboard. So that has been deleted. So this wire also deleted. Now I want to connect the multimeter in series. So I have to move. I'm moving using the arrow keys on the keyboard. That's a most convenient option if you want to precisely position the components using the arrow keys on the keyboard is it's the most convenient way to position the components in the circuit window. So again, now I connect the multimeter in series with R1 and R2. Now I want to measure the current. Okay. So here I pick ampere. Instead of voltage, I pick ampere. I will do the simulation. Again, see that the current in the circuit is 1 milliampere. 10 volt by 10K is 10 volt by 10K is 1 milliampere. Okay. So as expected, the current in the circuit is 1 milliampere. Okay. So let me stop this simulation again and let us do another circuit. Okay. So if you have any questions, please ask. Okay. You can unmute and ask if you have any questions. I think you simply have to watch this now because even if you have a software, it may not be able. You may not be able to watch and practice at the same time. You simply watch this. And at the end of the session, those interested can contact me if you need this software. I have an old version, so I'll share that software with you and also tell you how to install the crack. That way, you can practice at your home. So for the time being, I urge you to simply watch this. So let me delete this circuit. I select all the components and press delete. Next, let us study about an RC circuit. Let us introduce an RC circuit. Okay. So for that, I need a resistor. So I can directly access the resistor group from this clicking on the basic resistor. So I pick a 1K here. I pick a 1K resistor here. Now I want a capacitor also. So I pick a 1 mu of capacitor. I also need a ground. Remember, all circuits need ground, and ground is within the sources group. Within sources, power sources, ground. I pick a ground also. Okay. So to apply an input to the circuit, let me pick a function generator from the instrument toolbar. So here you see a function generator. I click on that function generator. I place it here. So function generator is now placed in the circuit. Now I want to connect these together. So I want to change the orientation of this capacitor. I want this C1 to be vertical. So for that, to change the orientation, you select the component, right click, and you see the option to rotate it by 90 degree clockwise or counterclockwise. So I click on that. Okay. So to change the orientation. Now the capacitor is now oriented in a vertical direction. Okay. So let me connect this to the capacitor. Now let me connect the positive of the function generator to R1 Okay, and the common to the lower terminal of C1, and I also connect the ground. Okay, so now I have an RC circuit connected to a function generator. If I double click on the function generator, you see the option to pick a waveform. It can be sine or triangle or square. Let me pick a square wave and let me select the frequency to say 1 kilohertz. I can also change the duty cycle or amplitude offset and so on. So I leave these values in their default value. So now I have a 1 kilohertz square wave with a 10-volt amplitude. Amplitude is 10-volt peak. I can also set the rise and fall times. Those are, let me leave those also at their default values. Okay. So now to observe the waveform across the capacitor, let me also pick a oscilloscope from the instrument toolbar. Within the instrument toolbar, you see an oscilloscope. Okay, I click on that and I place it here. Now I have an oscilloscope. Let me connect channel. This is a 2-channel oscilloscope. Let me connect channel A of the oscilloscope to the function generator and channel B to the capacitor. Channel B to the capacitor. I also have to connect the common to the ground. The common for channel A and channel B is connected to the ground. Okay. Let me simulate this circuit now. Simulate, and to see the output, let me double click on the oscillator. We can see some output. So I'm using 1 kilohertz. So let me adjust the time base of time base. Time base is now 10 millisecond per division. So let me reduce that to see the input and output waveform. I can reverse the background color here. Now I can see in a white background. And if you want to see only a single trace, you can click on single here. Okay. Otherwise, the trace is repeated. So let me click on the single trace here to see a single trace only. So I can see that the input is a square wave with a 10-volt amplitude, because channel A volts per division is at 5 volt. So 2 division is 10 volt. So this is plus 10, this is minus 10. Channel B is also at 5 volt. Channel B is also at 5 volt. So this is somewhere around 2 volt. Okay, 2 volt. So you can see that the capacitor exponentially charges and discharges in each half cycle. Okay. So in order to distinguish the channels input and output, you can change the color of a channel. Okay. So now if I change the color of the wire which connects the capacitor to channel B by clicking on this wire, right clicking that, I have to stop the simulation first. We stop the simulation, select this wire which connects the capacitor to channel B, select that wire, right click, click on color segment, and I can choose a different color for that wire. Say I choose this color for channel B. Okay. So now if I do the simulation, you can see that the channel B is displayed in that particular color which I selected for the wire. So that way it is easy to distinguish between channels A and B. Okay. So let me again pick single trace. Okay. So you can change the color. That particular channel will be displayed on the oscilloscope in the particular color that you select. Okay. So if I select this, stop the simulation, select this wire and right click, click on color segment, and if I pick green, now channel A will be displayed in green color. So click, you can see that channel A is now displayed in green and channel B is displayed in cyan. Okay. Let me stop the simulation again and let me modify this circuit a little bit. Let me change the now you have we selected a 1 kilohertz for this function generator, isn't it? 1 kilohertz is the frequency. So the time period is 1 millisecond. Now the RC time constant is also 1 millisecond. 1 kilo ohm into 1 mu of is 1 millisecond. So the time period is equal to the time constant. I have the situation RC is equal to T. Let me change the capacitance value to 10 mu of instead of 1 mu of. Let me select 10 mu of for the capacitance 10 U. Mu is represented by U. Okay. So now I have. So it says that you cannot modify the circuit while it is being simulated. So I have to first stop the simulation and then only the change will come into effect. So now I have RC is equal to 1K into 10 MF, that is 10T. RC is equal to 10 times the time period. Time period is 1 millisecond and the time constant is 10 milliseconds. So I have RC is equal to 10T. The time constant is 10 times the time period. So let us look at the oscilloscope again. Let us simulate the circuit again. Click on auto first, otherwise. So now you see that the capacitor voltage is very small because the time constant is very large. Time constant is 10 times the time period. So the capacitor can charge and discharge only a little within each time period. So to get a better display of the capacitor voltage, let me change the volts per division for channel B from 5 volt. Let me reduce that to it's a 200 millivolt. Now I can see channel B. The capacitor voltage is very small. It's only 200. The amplitude is only 200 millivolt because the time constant is very large. So the capacitor takes a longer time to charge and discharge. So within the 0.5 millisecond half time period, it can charge and discharge only a little. And you also see that the charging and discharging is almost linear. It appears linear because we know that the initial portion of the exponential charging and discharging curve is linear. The initial portion is linear. So the waveform looks almost like a triangular wave. The circuit behaves as a good integrator. Now on the other extreme, if I change the C value to from 10 μF, if I change to 0.1 μF, I have the case. Now RC is 0.1 millisecond. RC is 0.1 millisecond. So the time constant is very small compared to the time period. Okay. And in this case, what happens? What do you expect? Time constant is very small compared to the time period. So the capacitor can charge and discharge fully during each time period. Let us observe the output once again. So let me change the channel volts per division again. So both are now at 5 volt. You can see that the C charges and discharges fully within each time period. The capacitor can charge and discharge fully, isn't it? Because now I have RC is equal to 0.1T. We know that the capacitor changes takes 5 time constants to charge and discharge fully. So now we have T by 2 is equal to 5 RC. So within each T by 2 period, the capacitor can charge and discharge fully. Okay. So that's about a RC circuit. Now to make another modification, let me change this function generator waveform to sine. From square, let me change to sine, and let me do the simulation again and observe the output on the oscilloscope. Simulate again. You can see the output on the oscilloscope. So now you see that the capacitor voltage is the one in blue and the input voltage is the one in green. Okay, you can see that the capacitor voltage lags the input voltage. You can see that the capacitor voltage in blue, it lags the input voltage. So if you draw a phasor diagram for this low pass RC circuit, you can see that the capacitor voltage will lag the input voltage, and that is readily seen in this waveform. C voltage lags the input voltage. Let me stop the simulation again, and let me show some more features available in multisim. For that, let me delete the oscilloscope and the function generator, and instead let me place a AC voltage source here. So suppose I want to measure the frequency response of this circuit. I want to see how the capacitor voltage changes with frequency. Okay, so that's what we are going to see next. The frequency response of this low pass RC circuit. For that, I have to pick an AC source. Function generator is also possible, but for variety, I'll pick an AC voltage. So AC source is available within signal voltage. I'll pick a signal voltage source, AC voltage. Okay, pick an AC voltage, close. So the default is 1 volt peak, 1 kilohertz signal. I can double click on that and change the values, voltage or frequency. I can change by double clicking on this, but let me leave it at the default values. So now let me connect the AC voltage source to the circuit. Okay. I'll change this back to say 1 mu itself. Now I want to measure the frequency response of this circuit. For that, you have various analysis options available in multisim. Under the simulate menu, if you go to analysis, you see various analysis options available in multisim. Okay, frequency response can be determined using the AC analysis. Okay, within the simulate analysis, AC analysis. You click on AC analysis. So that will allow you to sweep the input frequency over a range. Okay, even though this frequency is selected as 1 kilohertz, under AC analysis, you are able to sweep the input frequency over a range. We want to see how the capacitor voltage changes as the input frequency is varied. So I have to specify the range over which the input frequency is varied. Say I want to sweep the input frequency from 1 hertz to say 1 megahertz. So I start frequency is 1 hertz and the stop frequency is 1 megahertz. Okay, frequency parameters. I'm sweeping the input frequency from 1 hertz to 1 megahertz. Okay, and I want to observe how the C voltage changes. So under the output tab, I have to select the capacitor voltage. Okay, here it is given current, some power, V1, V2, etc. are given. It is unclear what the C voltage is, whether it is V1 or V2. That is unclear. So let me cancel this for a moment and show you a different thing. Under options, sheet properties, you have this net names show all. Okay, under options, sheet properties, net names show all. Okay, so when I select show all, I apply and show all, you can see that some numbers appear. So okay, so these numbers are called net names in multisim. They are node numbers. The numbers are net is the multisim's name for nodes, and we know that what a node is. A node is a collection of points where we have the same voltage. Okay, same voltage. So this is node 1, this is node 2, this is node 0. Multisim will automatically choose the node numbers for you in the order in which you wire. I wired this one first. So this is 1, this is 2. Ground will always be node 0. So let me again go to simulate, analysis, AC analysis, and sweep the frequency parameters. I start frequency is 1 hertz, stop frequency is 1 megahertz, and let me go to the output tab. Output tab. Now I can see that the capacitor voltage is V1. Okay, voltage across the capacitor is voltage at node 1. So C voltage is V1. So I pick V1 and add it to the selected variables for analysis. V1 is selected into the variables for analysis. Now I click on simulate. I click on simulate, and you see the frequency response for the circuit. Here also I can reverse the background color. Here, if I click here, the background changes to white. And as expected, we can see that this shows a low pass response. Okay, you see the magnitude as well as the phase response. Okay, and you can see that the maximum gain is 1. Maximum gain is 1. Maximum gain is 1. Now suppose I want to measure the cutoff frequency of this circuit. Okay, I want to measure the cutoff frequency of the circuit. You can do that with the cursors available in this circuit. With the cursor, I can measure the cutoff frequency. When I click on this cursor, you see that 2 cursors will appear. 2 cursors will appear, and we know that by definition the cutoff frequency is the frequency at which the gain falls to 0.707 or 1 by root. Okay, so when I move cursor 1, I can see that x1 and y1 changes. When I move cursor 2, x2 and y2 changes. Okay, so the x and y position of cursor 1 is given by x1 and y1, and that of cursor 2 is given by x2 and y2. I am using this cursor to measure the cutoff frequency of the circuit. Okay, so when I am using cursor 1, when I move it to the leftmost side, I can see that the gain is nearly 1, 999 milli, which is nearly 1. Gain is nearly 1 at 1 hertz. The gain is nearly 1, and I know that at the cutoff frequency the gain will be 0.707. So how will I measure the cutoff frequency? I have to move this cursor 1 to the point where the gain is 0.707, and then I have to read off the corresponding frequency, isn't it? So the x and y position of cursor 1 is given by x1 and y1. So I have to move this where y1 is 0.707. I can read the value for y1 here. Y1 is now 470. I have to move cursor 1 where y1 is 0.707. Okay, 0.707, and I can read the corresponding. I cannot exactly position it at 0.707. I am not able to position that exactly at 0.707. I can position at 704 milli, which is 0.704. I can read the corresponding. X1 as 160 hertz. So that is approximately the cutoff frequency. Okay, at 704 at 160 hertz the gain is 0.704. Okay, another way you can try to position the cursor is select the cursor, right click on that, you can set an y value. If you set a y value of 0.707, the cursor will go to the point where the y value is 0.707. Okay, so you see that the cursor now goes to the point closest to 0.707, which is 706.69. Okay, because we are working on a digital computer, even though this curve is shown as a continuous curve, actually the analysis is done only at discrete frequency intervals. That's why we are not able to go to exactly 0.707. Okay, even though this curve is shown as a continuous curve, the actual analysis is done only at discrete frequency points because we are working on a digital computer. And you can read the corresponding x1 as 159 hertz. So that is the cutoff frequency for this circuit. Okay. See, remember what I did? I select the cursor, right click, and set the Y value as 0.70 as 0.707. So let me draw BJT circuit next. And you can, another analysis is transient. So let me replace this with the DC source and show another analysis option available in alternate. This was our previous circuit. I want to replace this with a DC source and see how the capacitor charges. Double click on this, click on replace power source. I selected DC power, so that that AC source has been replaced with a DC source. Now let me change the voltage to 10 volt, and let me show another analysis. Under simulate analysis, you see transient analysis. You see transient analysis. So we can see that the time constant is 1 millisecond. R is 1K into 1 mu f is 1 millisecond. So let me, and I know that a capacitor will take nearly 5 time constants to charge fully. So 5 time constant is 5 milliseconds. So let me do a transient analysis on the circuit from 0 to say 10 milliseconds. So the start time is 0 and the stop time is 0.01 second, which is 10 milliseconds. Okay. To understand why I chose 10 milliseconds, I know the time constant is 1 millisecond. I know that the capacitor will take approximately 5 time constant to charge fully, which is 5 milliseconds. So I choose 10 milliseconds. So the point here is that you cannot rely. You need to know some theory also to be able to use the circuit simulation software. If you know nothing about how an RC circuit works, how will you choose the appropriate stop time, end time for the simulation? So these are actually computer aided tools. You cannot completely rely on this simulation software. You need to know the working of this circuit. That's why these are called computer aided analysis, computer aided design. So these tools are not a replacement for the human brain. You need to have an idea about the operation of the circuit. Then only you can successfully use these tools also. Here we see an illustration of that. Without knowing how much time it will take for the capacitor to charge fully, we cannot choose an appropriate value for the stop time. Okay. So the point is that you may be tempted to think that since we have this simulation software, what is the need to study all the theory? What is the need to study how the RC circuit works? The answer is that's not correct. It's like using this software without any knowledge of theory is like giving a calculator to kindergarten students without learning addition, what addition is and what subtraction is. If you say that we have a calculator, then no need to study addition and how to manually do addition and subtraction. That will not work. No, you need to, once you get the result, you go to have some idea whether the result is correct or not. If you have no idea about addition or subtraction, and if you make some mistake while doing the entry, doing the data entry, and by looking at the result, you should be able to tell that I made some error in the data entry. Similarly, while using these tools also over a long period of time, you might make some data entry error. So by seeing the result, observing the result, you should be able to tell that, okay, so this circuit is not working as expected. I made some error. To say that, you should have some knowledge about how the circuit works and what the expected output is. So the point is that these tools are for aiding the human brain. These are not replacement for human brain. Human brain is not obsolete. Even with the availability of these tools. Okay, so wisely I have chosen the end of analysis as 10 millisecond, and for output I have to choose. I want to see how the capacitor voltage varies with time. So I choose V1. I know that capacitor voltage is V1, voltage at node 1. This is node 1. So I choose, click on V1, add it to the selected variable for analysis, and click on simulate. Sorry, something happened. Let me redo the analysis. Simulate, analysis, transient analysis, analysis from 0 to 10 millisecond, and analysis parameter. I will choose set to 0. Okay, initial conditions are set to 0. So initial condition means here the initial condition is the capacitor voltage. I have to set the initial capacitor voltage to 0. I assume that the capacitor is initially uncharged. So I set the initial condition to 0 and I click on simulate. So I see that the capacitor voltage rises from 0 to 10 volt. 0 to 10 volt in 10 millisecond. I did the analysis from 0 to 10 millisecond. I can see that in nearly 5 millisecond, 5 time constant, capacitor voltage is nearly 10 volt. Okay. So shall we switch to digital or some transistor circuits? I think we'll switch to some digital because we have mentioned analog and digital circuit simulation. Let me switch to digital. Let me first verify the working of a NAND gate. So NAND gates are available within the TTL family. You click on TTL, and within the TTL group, I see several families, and the family that we commonly use in our laboratories is the LS family, which stands for low power short key. So I click the LS family, and let me pick a 74LS00, which is a NAND gate. I click on OK. So a 7400 IC has 4 NAND gates in it. So that's why it's showing A, B, C, D. Let me pick one NAND gate, A. So I place it here in the circuit window. So I have placed a NAND gate in the window. Now I want to verify the operation of this NAND gate. So for that, let me pick a so from sources, let me pick digital sources, and let me pick an interactive digital constant. Interactive digital constant. I need one more interactive digital constant, and to indicator, I need to display the output. I need an indicator. I pick a probe. I pick a digital probe. I pick a digital probe. Okay. So let me connect the interactive digital constants to the NAND gate and the digital probe to the output. Okay, so I can these are interactive digital constant. I can change the state from 0 to 1 using the mouse or using this key. You can also change this key. I can change the key from space to any other key, or using the mouse I can change the digital state from 0 or 1. Okay, so that's why it's called an interactive digital constant. So let me simulate this. I can see that when both inputs are high, output is low. If I make one input as low, I can see that the output is high. When both inputs are low also, output is high. So only when both inputs are high, then AND gate output is low. Okay. So that way I can simulate a digital. I can verify the working of a NAND gate. So next, let me make a SR latch. So I can pick another component which is already in the circuit from this in-use list here. From this in-use list, I pick another 74LS, and let me pick another indicator. Sorry, not the interact. I'll pick another digital probe. And let me wire a, let me delete this, and so I can modify the wire shape. Say if I want to make it look more neat, I can select the wire, then drag it like this. This also again. Okay, so now I have an SR latch here. So let's again name this. Uh, I can call this label this as S bar. I can label this as R bar. And label this as Q. And this as Q bar. So let me simulate this. Both are low, and if I make S bar low, you can see I observe that Q has gone high. If I make S bar high, there is no change. If I pull R bar low, I can see that the latch has been reset. Q is 0 and Q bar is high. So that way I verify the working of the SR latch. So if I make both these low, I see that we reach an invalid condition when both S bar and R bar are low, both Q and Q bar are high, which is an invalid state. Maybe I can add another two gates and make this an I can convert this into an gated SR latch, or since the time is running out, let me illustrate a flip flop. Let me pick a flip flop. Say I want to verify the working of a 7473 JK flip flop. Okay, 7473 JK flip flop. Okay, so this JK flip flop IC has two JK flip flops in it. So that's why it's showing A and B. Let me pick one JK flip flop and close it. So again, using interactive digital constants and digital probes, I can verify the working. Interactive digital constant, one for J and one for K, and then let me pick a probe from indicator probe, digital probe, one for Q, another one for Q bar, and K. So there is also a clear. I'll pick another interactive digital constant to wire the clear. So you need to connect a clock also. There is a digital clock available within source. Within digital sources, there is a digital clock available. Anyway, to verify the working, let me use a different arrangement. Let me pick a VCC. And digital ground. And from basic, let me pick a switch. Let me pick a single throw, double throw switch. Close it. And let me invert the orientation of this. I'll flip this horizontally and connect this switch to the clock. Connect one end of the throw to VCC and other end to the ground. So clear is active low. So let me disable that clear and make it active high. See, hope you can see I connected J and K to interactive digital constant. Clear also to interactive digital constant. I have connected the Q and Q bar output to digital probes, and I have connected the clock to a SPDT switch like this. Okay, so let me run the simulation. Now I see that the flip-flop is cleared. Let me make, I want to set the flip-flop. I want to make Q high and Q bar low. So for that, I make J1 and K0. So we can see that nothing happens because 7473 is an edge triggered flip-flop. Flip-flop changes state only during the negative edge of the clock. So we can simulate a negative edge by moving this switch from VCC to ground. Okay. That is why I have used a switch here. We can simulate a negative and positive edge by moving the switch between VCC and ground. So I have made J1 and K0 in order to set the flip-flop. I want Q1 and Q bar 0. But that happens only when I click on this switch. I see that the flip-flop has been set. When I move the switch from VCC to ground, what happens? That simulates a negative edge going from high to low. So the flip-flop change state then at the negative edge of the clock. Now I want to say I want to reset the flip-flop again. For that, I change J back to 1 and K to J to 0 and K to 1. And let me change the, I click the switch. When I click, the switch moved from ground to VCC. That simulates a positive edge. Nothing happened during the positive edge because 7473 is a negative edge triggered flip-flop. Nothing happened. Flip-flop resets only during the negative edge. So now next I am going to simulate a negative edge by clicking the switch again. So from VCC to ground, we see that the flip-flop reset. Okay. And if both J and K are high, we know that the flip-flop will toggle. So if I click the switch repeatedly, what happens? Let us see what happens. This is a positive edge, nothing happens. Click again, that is a negative edge, changes state. Click again, will be a positive edge, nothing happens. Negative edge, we can see that the flip-flop changes state only during the negative edge of the clock. Negative edge of the clock. So we understand that the 7473 is a negative edge triggered flip-flop. And similarly, you have other flip-flops also, D flip-flops. All other types of flip-flops are here. So let me select this and delete. And let me try to quickly show 7474 set D flip-flop. Okay. I'll pick another 7474 and let me try to wire a ring counter quickly. Where is an indicator? I'll choose an indicator, little probe, another indicator. Sources, I pick a digital clock. Then I need some interactive digital constants. One for clear and one for preset. I connect the digital clock here. So these ICs have some preset and clear inputs. Let me tie the preset of this with the clear of this, and I'll connect to this switch. And the clear of this, and preset of this too. So I have wired a ring counter. Let me, in order to see the output, I change the clock frequency from 1 kilohertz to 1 hertz. Then only I'll be able to see uh, the output. So we simulate this, and I preset and clear are also active low. So to disable, make this. So I can see that the we have wired a ring 2-bit ring counter. Okay, I have connected the preset of this to the clear of this. Then I have made it low. So what happens? This one became set and this became clear. So I am started with the state 1-0. Then I pulled it back high. So it started the simulation. So you can also simulate transistor, BJT, FET, MOSFET circuits, and also op-amp. 741 op-amp is also available. So you can simulate a wide variety of analog and digital circuits using multisim. I think I'll stop here. And if you have any questions, please you can ask. If you have any questions, please ask. If you need to know anything, please unmute and ask. Anything to know? Shall I stop or and if anyone wants this software, I can provide a link and also show the crack. So let me illustrate that also, how to install this software.
Sir, excuse me,
Yes.
sir.
Yes, please ask.
In the circuit simulation, what we did, sir, that JK flip-flop is a clocked JK flip-flop,
Yeah.
right, sir?
Yeah. 7473.
Okay, sir. It's a clocked JK flip-flop. It is going to act in negative edge triggered or negative edge triggering
It's
mode.
a negative edge.
But whenever
7473.
both J and K's values are 1,
Yeah.
it should toggle or it is going into race run condition, but is not happening in the circuit.
No, it does not. It toggles only once. It's an edge triggered flip flop. So at every negative clock edge, it will toggle once. Because it's an edge triggered. Race around is not present in edge triggered flip flops. Okay. So it
is not present. But
Yes.
by by 5% initially it is slightly toggle.
It toggles only once. At every negative
Once.
clock edge, it toggles only once.
Once. Okay,
That's
sir.
how
Okay. Thanks, sir.
that's how a negative edge triggered flip flop works.
Okay.
So
Thanks, sir.
we go to edge triggered flip flops to avoid this race around condition.
Okay, sir. Okay. Thanks, sir.
And all the practical flip flops that we use in laboratories are edge triggered. 7473, 76, 7474, etc. All are edge triggered flip flops. And any other question?
No, sir. No, sir. Thank you. Thank you so much, sir.
Any other
Hi,
question?
sir.
Yes.
Okay, okay. Thank you, sir. Any other queries, please? Otherwise, we can wind up our section. Any other queries? Okay. Okay.
Okay. Thank you. Thank you.
Okay, dear participants, we are concluded. We are going to conclude our section. Our section on analog and digital circuit simulation. I would like to thank you, Mr. Arun Varghese, sir, Associate Professor, for this wonderful section on this simulation. Thank you, sir. Thank you very much.
Thank you. Thank you. Thank you for giving me this opportunity to conduct this session. Thank you, Ranjit and Shinu and the Department of EC, Mount Sion College of Engineering, Kadammanitta. Thank you for this opportunity.
Okay, thank you, sir. And I also want to say thank you to all the participants from different colleges, also from our colleges, especially faculty members, students, and also industry leads are also participated in this webinar. I would like to thank you on behalf of our college, department, our HOD. I would like to thank you, each and everyone who attended this webinar. We also shared a Google form in the chat box. Please fill up that fill up that feedback form. Okay. After that, you can sign out from the webinar. Okay. Feedback form is on your chat box. Please fill the feedback form. Thank you, everyone. Thank you, sir.
Thank you. Thank you once again. Thank you.
The feedback form is for your certificate generation. Your certificate will be provided within couple of days.